Chapter 3 introduces the idea of measuring angles in radians. Some of us are going to be more familiar with the radian measure than others, but it is a more common angle measurement for trigonometry. So what is a radian? Great question. An angle with a vertex at its center of a circle that intercepts an arc on the circle equal in length to the radius of the circle has a measure of 1 radian. Ooh, that's a lot of words. Let's discuss what that means. So, like the fact that a degree is 1/80th of a semicircle, a radian is a unit of measure that is equal to the same distance along the arc of a circle. So for instance, in this first circle, this is my radius r. So this is the same distance curved along the circle as r. That means that if I were drawing this circle differently and my terminal angle was here, that would be the angle of 1 radian. But since in this circle we have doubled that length, there's 2 radius lengths curved around your circle, this theta is 2 radians. If I just kind of highlight that same space, so this is r and we have r curved around the circle, if I was a better artist this would be more precise, but this is half of that whole distance, so this is half of a radian. Now what's interesting about radians is that when we measure them all the way around the circle, this is me putting in 1 radian at a time, we end up with 6 radians and a little bit more. Now that little bit more, if we were to just round it to 2 decimals, would be 0.28. If you're starting to recognize these numbers, that's 2 times pi, which would be 6.28-ish. And so all the way around a circle, 360 degrees, is 2 pi radians. So what that means for us is that when we are measuring theta, the central angle of a radius r, and that theta intercepts the circle with an arc length of s, so we're going to have an arc length s with this theta and r, we can write a formula that theta is equal to s divided by r. Kind of didn't leave enough space there to write it, so sorry. So if I was writing that in words, we would say that theta is equal to the arc length, so that's the curved distance, divided by the radius of that circle. Now there's some conversions between degrees and radians. So a lot of us throughout this class are going to initially think about angles in terms of degrees because that's probably what you're more comfortable with. I would like for us to get comfortable about thinking about angles in terms of radians to begin with. But while we're converting or translating back and forth that language for ourselves, let's look at the conversions between degrees and radians. Like I said earlier, a first full circle, 360 degrees, is 2 pi radians, which means that half of a circle, 180 degrees, is just pi radians. Half of that. We can go further to say that 1 degree is the same as pi over 180 radians, in the same way that 1 degree is 1/180th of a semicircle. If that semicircle is pi, we just divide that by 180. Or vice versa, 1 radian would be 180 divided by pi. Now these last 2 measurements right here are going to be helpful for our actual conversions between degrees and radians. If you have a degree and you want a radian, you're going to multiply that by pi over 180 and simplify to convert to radians. If you have a radian and you want degrees, you're going to multiply by 180 divided by pi degrees and simplify. So these 2 conversions are going to be very helpful for you. For my class, these concepts are probably going to be added to your formula quizzes coming up soon. So let's see some examples of converting from degrees to radians. And we're going to leave these things, for the most part, in fraction form and in terms of pi. There are times that we're going to round to decimal radians, and we'll see some examples of that through and through. To convert 45 degrees into radians, I would take 45 degrees and I would multiply it by pi over 180. Now we're going to do this by hand without the use of a calculator because we're going to keep this in fraction form. Giving 45 degrees a denominator of 1, we'll realize I can just do top times top and bottom times bottom. That means this is 45 pi over 180. And then I just need to reduce that fraction, leaving it in terms of pi, which means the pi should stay in your final answer. My brain initially saw that 45 and 180 are both divisible by 5. That's just what my brain saw first. So 45 divided by 5 is 9, and 180 divided by 5 is 36. Now both of these numbers can continue to simplify down. Maybe you saw this simplification another way. 9 and 36 are both divisible by 9, so 9 divided by 9 is 1. 36 divided by 9 is 4. So 45 degrees is pi over 4. Those of you who know your radians and your degrees and know them interchangeably, this will look familiar to you. But let's say we're giving you a degree measurement that's maybe not so familiar. So we will need to use the conversion factor to convert negative 270 into radians. We take the number negative 270 and we multiply it by pi over 180. It's like we're adding the pi into it, so we're multiplying the pi on the top. So we're going to put that over 1. This is negative 270 pi over 180. Again, all we're doing is reducing those fractions. I noticed first that the top and bottom both have an extra 0 on them, so I'm going to take that down to negative 27 over 18. Ooh, and both those numbers are also divisible by 9. Negative 27 divided by 9 is negative 3, and 18 divided by 9 is 2. So negative 270 degrees is negative 3 pi over 2 radians. We can also do this for decimal values, decimal degrees. Changes nothing about what we do. We'll still do 249.8 degrees. I forgot my degree sign over here. Multiplied by pi over 180. And if we put this into one fraction, this would be 249.8 pi over 180. Now at this point, that would be pretty much the simplified fraction we could do by ourselves. You can chunk this one into a calculator using 249.8, the pi button, and then dividing by 180. You'll get approximately 4.3598 radians. Both are acceptable answers, whichever one the question is asking for or seems most appropriate for the problem. What if we go the opposite way? I've given you this time radian measures, and I want you to convert to degrees. The reason I know that they're radian measures, number 1, is that I see a pi there, and number 2 is that there is not an actual degree symbol there. So we use the conversion factor, but the reciprocal. So 9 pi over 4 to convert to degrees, I'm just going to multiply by 180 divided by pi. I remember that it is this conversion because I want the pi's to be able to cancel out. If the pi's cancel out, you are successfully converting back to degrees. So this is going to end up being 9 times 180 divided by 4. But let's make this easier for ourselves. 180 and 4 are both divisible in my brain by 2. So if I just reduce those, that's going to be 90 divided by 2. And again, 90 is also divisible by 2. I should have seen that coming. So this is actually 9 times 45. 9 times 45 is 405 degrees. So obviously this is me trying to show you my work on how I did this in my brain. If you're in a calculator part of the test or I'm giving you a calculator, just go here and pop those numbers in a calculator. It will reduce to 405 degrees. In part B, again, doing this by hand, so we're going to reduce these numbers without the use of a calculator. We're going to multiply negative 5 pi over 6 by 180 over pi. I remember I want this to happen because I want the pi's to cancel out. This will end up being negative 5 times 180 over 6. Now, my brain notices that 180 and 6 are divisible by each other, so this is actually going to end up being negative 5 times 30, because 180 divided by 6 is 30, which means this is negative 150 degrees. Now, part C might be throwing up your spidey senses, because I told you when you're converting from radians to degrees, your pi's should cancel out. But there's no pi in this one. We're still going to use the measurement 180 divided by pi because this is a radian measure. It is not a degree because there's not a degree symbol right here. That's why I was being so picky about that in the first 2 chapters of putting your degree signs there. Otherwise, you're talking about radians. At this point, we would actually just go ahead and in a calculator multiply 4.25 times 180. We would get 756 divided by pi. And again, throwing that into a calculator so we can see degree measures, this is 243.5071 degrees. Now this next little bit is super important. Again, it's just kind of what I said. It says, if no angle measure is indicated, no unit of angle measure, meaning you don't see the little symbol for degrees or it doesn't say it is in degrees, then the angle is understood to be measured in radians. This is actually the default mode for angles. No unit of measure means we are measuring in radians. So for example, the figure below shows an angle of 30 degrees. Notice the degree symbol. And the figure on the right shows an angle of 30, which means 30 radians. These are significantly different angles. 30 degrees is this cute little acute angle, and 30 radians loops all the way around multiple times and ends in quadrant 4. They're not even coterminal with each other. So we have to make sure we're using the correct degree or radian, and you're telling me exactly right whether it's degree or it's radian. That's super important to me. What's also super important is knowing the different degrees and exact radian values for our special right triangles and our quadrantial angles. So we, in our table that I had you memorize in chapters 1 and 2, I had 0, 30, 45, 60, and 90 degrees in that table. Well, now I need you to automatically know the exact radian values for each of these special right triangles and my quadrantial angles for quadrant 1. We just need to know these back and forth. So if I say 30 degrees, you should know immediately I'm talking about pi over 6. These are going to be something that will show up on your next formula quiz, these exact values. I also would like for us to extend that knowledge to the other quadrantial angles. So 180 degrees is pi, 270 degrees is 3 pi over 2, and 360 degrees is 2 pi. So those things I've highlighted here, the exact values in radians for the different important degrees in quadrant 1 and your quadrantial angles, those will be added to your formula chart. Now, of course, those are not the only angles that we're going to be working with in radians. If you look at the next page, we're also going to be working with all of the angles around a unit circle, around just a full revolution of a circle. In degrees, we have 30, 45, 60, and 90 from quadrant 1. But if we extend past quadrant 1, we were doing 120, 135, 150, 180, and on all the way around the circle. Well, I need us to start recognizing that we not only can count now or measure in degrees, but we can also measure in radians. So we have pi over 6, pi over 4, pi over 3, pi over 2. And then we double pi over 3 to get 2 pi over 3, since 60 is double it, you get 120, and on and on. So these numbers are going to change as we go around the circle. These will help us eventually fill out a unit circle and decide our reference angles when we're outside of quadrant 1 in radian mode, not just in degree mode. So use this as a reference as you're starting to memorize where these angles are around a circle. There are some patterns we'll go over when we're not just doing a video lesson for this chapter. So let's find some exact values outside of quadrant 1. Okay, tangent of 2 pi over 3. So first things first, I'm not going to scroll up to it, but you can look up at your paper. What quadrant is 2 pi over 3 in? Since 2 pi over 3 doesn't quite make it all the way to pi, or 3 pi over 3, this is a little bit less than a semicircle, which means this is in quadrant 2. Therefore, since we know it's in quadrant 2, when we look at the reference angle, or just regular tangent of pi over 3, where to get this from? I just lost this value and used pi over 3. That's going to be your reference angle. But in quadrant 2, tangent is going to be negative. So I need to make sure I'm remembering to make this negative. Now, based on our conversion factors, because we're still converting into degrees right now while we get comfortable with radians, this is exactly like me asking you, what is the negative tangent of 60 degrees? Well, you know that the tangent of 60 degrees is square root 3, which means you just pop that negative in front of it. So the tangent of 2 pi over 3 is negative root 3. it is the same as the negative version of tangent of pi over 3 or the negative tangent of 60 degrees. Following the same process for part B, what quadrant is 3 pi over 2 in? Hopefully you're not quite sure how to answer that because that's actually one of my quadrantial angles. So that means it's on my coordinates. It's either 0, 90, 180, or 270 degrees. It's like one of my axes. So that means that we just need to think about the coordinates there. Sine is the y coordinate, which means when we're looking at the downward y, we're going to be looking like it's negative sine of pi over 2. Now again, if we convert this to degrees, just while we're getting used to thinking in radians, this is the sine of 90 degrees. Well, the sine of 90 degrees is 1, which means if we make that negative, for the fact that this is not the positive 90, but all the way around at 270, we would get negative 1 as our measure of sine of 3 pi over 2. The cosine of negative 4 pi over 3, what quadrant would this be in? So since we're going the negative direction, you're counting 4 pi's over 3 clockwise. I'll show this one. So if I'm counting pi's over 3, this is 1 pi over 3, 2 pi over 3, 3 pi over 3, negative 4 pi over 3. So we're all the way here in quadrant 2. It matches up and is coterminal with positive 2 pi over 3. Keep that in mind as we work. So like I said, this angle is in quadrant 2. In quadrant 2, we know that cosine is going to be negative. So when we're working with this, we have to make sure that we know that it's going to be negative. If I think about the acute angle measure that matches this, this is like the negative cosine of pi over 3. Where'd that negative come from again? Remember, in quadrant 2, cosine is negative. Again, while we're thinking in degrees, because that's what we're comfortable with right now, pi over 3 is 60 degrees. Cosine of 60 degrees is 1/2, so then we would just make it negative. And cosine of negative 4 pi over 3 is negative 1/2. Before we leave this page, if you're sitting here going, man, Miss Quigley, how do you know which one is positive, which one is negative? Remember when we learned about the quadrants, we knew that all of the trig functions are positive in quadrant 1, only sine and its reciprocal, only tangent and its reciprocal in quadrant 3, and only cosine and its reciprocal in quadrant 4. The acronym I was using is All Star Trig Class, which is what this class is. If you've taken this class before, you may have used the acronym All Students Take Calculus. Either way, that's where I'm getting the positivity or negativity of each of the trig functions that we did down here.